Hello everyone, welcome to my channel. In this lecture, we will discuss about the separation of methane and carbon dioxide using the aspen adsorption. So, the separation of methane and carbon dioxide using the aspen adsorption. So, we first of all we will open the aspen adsorption, and here go to the component list. Click on this one and click on add component. So here you can I will click on configure property. So click on use aspen property system, click on edit using aspen property. So here we will add the component which are methane and carbon dioxide. We will use these we will add these component from the aspen plus. So it will take some time. We will add the component which are the carbon dioxide and methane gases. We will separate these gases with the help of aspen adsorption column. So usually in aspen adsorption, we will use some activated carbon or some other adsorbent to separate these components. So here we will add the component which is methane CH4 and second one is carbon dioxide. Now click on next and here select the property method. So here I will select the click on all and here I will select the Finn Robinson. So select the Finn Robinson equation of state. Now click on next and click on OK. Now open the aspen adsorption and click on OK. Click on the aspen property and click on yes. So the property, the component are added. Now click on aspen adsorption and here go to default and click on default. Here you can see these are the component which are added from the aspen plus. So click on the double arrow to add the both component methane and carbon dioxide. You can add them one by one by clicking on this single arrow. So I'm adding the two component which is methane and carbon, which are methane and carbon dioxide. Now click on OK. So our component are added to the aspen adsorption. Now we will make a blue sheet. So this is the gas speed. Here you can see, click drag and drop this one gas speed. This is the gas bed and this is the gas product. This is the gas bed. There are two well. So the gas well, this is the gas well, this is for feed and this is for the product stream. Now connect the stream. So here you can see this is the connection. Here you can see gas material connection. Click on this one and here you can see connect all the stream. So the feed is connected with well, feed well, it is connected with the adsorption column. Then the product of adsorption column is connected to the product well and the product well is then connected with stream number B3. Okay, you can give name to these. So here suppose I'm click on well and rename block. So this is the feed well. This is the rename block product well. Okay, product well. This is the feed. B1 is feed. So this is feed. So we can rename the feed. Suppose I'm rename the block. This is feed. This is product. rename block. This is the product. Okay, feed and product. Okay, now go to the feed and specify the feed condition. So double click on feed, and it is reversible. The model type is a reversible pressure setter, and an enabling report is true, and the flow unit is mole. Okay, click on specify, and here specify the feed condition. So we will add some data from this this one. So we will go to the feed specification. Here this is the okay feed specification. Okay, this is speed specification. So here model type is reversible pressure setter and flow rate is free. The composition of methane in the forward direction. So it is 0.62. So the composition of methane, here the composition of methane, this Y is composition of methane in the forward direction. So it is in kilomole per kilomole. Okay, it is 0.62. And remaining is carbon dioxide. The mole fraction of carbon dioxide in the forward direction is 0.38. The temperature is 298. Okay, it is 290. Suppose it is 290, and the pressure is 3 bar. Pressure is here, the pressure is fixed, it is 10 bar. Okay, now close this one. Close this one and go to the a product specification. Click on a product, and here specify. So click, go to the product side. The product is a reversible pressure setter, and the composition of methane in the forward direction is, in reverse direction is 1. So here you can see is favor methane, and there is no carbon dioxide. In the reverse direction, the temperature and pressure value are, the temperature is same and fixed, and the boundary pressure or the pressure is 9.95 bar. So the temperature is 290, and the pressure is 9.95 bar. 9.95 bar. 9.95 bar. Okay, close this one. Okay, now go to feed well. Click on this one, and the reverse flow setter, reversible flow setter, it is linear well. And okay, specification mode made available is the flow or CV. So we will go to the specification, and here the active specification, C value and the flow rate. So the feed well, we will go to the feed well. Okay, this is the inlet well, which is feed well. So active specification is 3, and CV value is 100 kilomole per second and 2 bar. So active specification is 3 for feed well. Active specification is 3. Here, when the active specification value is 0, you can see it is off. The valve is off. When active specification value is 1, the valve will be open. But when active specification value is 2, uh, 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 2, so it will be show us some flow rate, or for flow rate we can also give some, the flow rate is 3. For example, if active specification is 3, then there will be some flow rate, there will be some flow through the well. Now the C value is 100. The C value here is also 100, and the flow rate is the 8 multiplied by 10 raised to the power minus 7 kilomole per second. So 8 multiplied by 10 raised to the power 10 raised to the power minus 7. 8 multiplied kilomole per second. Okay. Now go to the product well. Click on this one. Click on specification, and here the active specification value is 1. It is 1. So it means that the well, this well is open, and the C value is 100. So the C value is 100. Okay, and here you can see the flow rate is 0.05. 0.05. Okay, close this one. Close this one. Now go to the bed, double click on bed 2. This is the adsorption column. So there will be some activated carbon or some other adsorbent material. The bed is vertical direction and the number of layer within the bed is 1. There are 1 layer. So if, for example, if I want to add a 2 layer, so I will add 2 here. Here you can see there will be two layer will be formed. This is layer 1 up to this position and this is layer 2. So I want layer 1 simply. This is layer 1 here and it is in one dimensional and there is no heat exchanger. Okay, double click on this one, close this one. Okay, close this one, double click on this one and here this tab will open. Configure block stream bed 2 layer. So this bed 2 is the adsorber or adsorption column. So here the discretization method is UDS1 and the number of node is 20. You can change the number of node to 30, 40 depend on your problem. So I will go to the bed. Okay, okay, okay. I will go to the bed. Here you can see the bed. This is the constant parameter for the bed. So okay, for the bed, and these are the okay. The discretization is UDS1 and number of node is 20. Here you can see the momentum balance. So this is the general UDS1 and 20. Now go to the momentum balance. So it is convection and argon equation. You can change the equation like Karman-Cousins equation and Darcy equation or some other. So here I will follow this book. So here you can see the momentum balance is convection with estimated dispersion. So material balance is convection with estimated dispersion. Click on this one, convection with estimated dispersion, and the moment, this is the material balance. Material balance is convection with estimated dispersion and momentum balance assumption is argon equation. Okay, now kinetic model, go to the kinetic model. This is the kinetic model. The film model assumption is solid. Okay, the kinetic model assumption is lump resistance. Okay, the form of lump resistance model is linear and the molecular diffusivity is fixed and the mass transfer coefficient is also fixed. Okay, mass transfer coefficient is fixed, lump resistance is linear, kinetic model assumption is lump resistance, film model is solid. Okay, it can be solid or fluid depend on your problem. Here it is solid. Now go to the isotherm. So here I will go to the isotherm. Here this is Langmuir 1. So Langmuir 1, the Langmuir 1 and Langmuir 2 depend on temperature. Okay, so I will go to the Langmuir, extended Langmuir. Here you can see the isotherm model is extended Langmuir 2 and the isothermal density is on partial pressure because the methane and carbon dioxide are gaseous components, so we will use the partial pressure. For liquid, like for the adsorption of heavy metal ions or for the adsorption of methylene blue or dye, we can use the concentration is a function of the concentration function. So we here we will use the partial pressure. So extended Langmuir 2, we will use the extended Langmuir 2. Here you can see extended Langmuir 2 and the isothermal density is concentration or partial pressure, so we will use the partial pressure. Now go to the energy balance. So this is isothermal. This is isothermal problem. Okay, here you can see the energy balance assumption is non-isothermal with gas and solid conduction. So non-isothermal with gas and solid conduction. Non-isothermal with gas and solid conduction. Okay, and heat transfer to the environment is adiabatic. Okay, heat transfer to the environment is adiabatic. Okay, here you can see the heat transfer to the environment is adiabatic. Okay, now click on specify. Here here you will add the information about the bed dimension, the bed height, the diameter of the bed, the adsorbent particle radius, sphericity, etc. So here we have information about the bed. So we will go to the specification, to table 14. Here you can see the height of the bed is 0.163 0.613 meter. so 0.163 meter, and the internal diameter of the adsorbent layer is internal diameter of adsorbent layer is 1.6 centimeter. So it is 1.6 centimeter. Go to centimeter. 1.6 centimeter. 1.6 centimeter. Now the interparticle voidage. So the interparticle voidage, here you can see the interparticle voidage is 0.52 and the intraparticle voidage is 0.59. 0.52, 0.59. The bulk density of the adsorbent. So the bulk density of adsorbent is, here bulk density of adsorbent is 515.93 kilogram per cubic meter. So 3 kilogram per cubic meter. The adsorbent particle radius, the adsorbent particle radius is 0.7 mm. So 0.7 millimeter, 0.7 millimeter, 0.7 millimeter. The adsorbent shape factor is 1, and here the constant mass transfer coefficient. So the constant mass transfer coefficient for methane is 5, and for carbon dioxide is 110. For methane it is 5, and for carbon dioxide and its unit is its unit is 1 divided by second, the reciprocal of a time. So the mass transfer of methane is 5 and its unit is 1 divided by second, and it is for carbon dioxide is 110. Then the molecular diffusivity of the methane and carbon dioxide. The here there is no information. So this is this information is the adsorbent specific heat capacity. The adsorbent specific heat capacity. So we will go to the adsorbent specific heat capacity. So here the adsorbent specific heat capacity. Okay, this one, adsorbent specific heat capacity, this one, CPS. So its unit is the adsorbent specific heat capacity. Here you can see its unit is in joule per kilogram into Kelvin. Joule per kilogram into Kelvin. So I will change this unit, joule per kilogram into Kelvin, and it is here you can see it is 1000. Okay, okay, it is 1000 here. Okay, the constant of heat of adsorption, this is the heat of adsorption for methane, and this is the enthalpy of adsorption or heat of adsorption of methane and carbon dioxide. So heat of adsorption of methane is here you can see it is minus 1.8. So I will uh, copy this one. Methane is, and its unit, here you can see the unit is joule per kilomole. So I will change the unit first of all, joule per kilomole. Joule per kilomole. For carbon dioxide, unit is also joule per kilomole. I will paste the minus 1.8 multiplied by 10 raised to the power 7 for the methane, and for carbon dioxide it is minus 2.26 multiplied by 10 raised to the power 7 minus 2.2 multiplied by 10 raised to the power multiplied by 10 raised to the power 7. Okay, the this one is the constant of heat transfer coefficient. This is the heat transfer coefficient. So so I will assume this one because there is no information. Now the constant of gas phase heat conductivity, the constant of gas phase heat conductivity in watt per meter into Kelvin. The constant of gas phase heat conductivity. So gas phase heat conductivity, constant of gas phase heat conductivity, and its unit is, here you can see unit is different. So I will use watt per meter into Kelvin, watt per meter into Kelvin, this one, and its unit, here you can see the unit is 0.025, 0.025, 0.025. Okay, the absorbent thermal conductivity, adsorbent thermal conductivity. Okay, adsorbent thermal conductivity is also given 0.6 watt per meter into Kelvin. Watt per meter into Kelvin. Again, watt per meter into Kelvin. 0.6. 0.6. Okay, the specific surface area of the adsorbent and 1 divided by meter. It is 2057.14. Specific surface area of adsorbent and 1 divided by meter. So 2057.14. Okay. Okay. Now isothermal parameter. Go to the isothermal parameter here. Isothermal parameter for IP1 mean isothermal parameter of methane, isothermal parameter of carbon dioxide, isothermal parameter 2 for methane, and similarly for carbon dioxide is isothermal parameter 3, 4, etc. So we will add these value. So isothermal parameter 1 for methane is this one, 6.31 multiplied by 10 raised to the power minus 6. So this is isothermal parameter 1. Here you can see isothermal parameter. So I will copy and paste 6.31 and here multiply by 10 raised to power minus 6. 10 raised to power minus 6. For carbon dioxide, it is 1.27. 1.27 multiplied by 10 raised to power minus 5. And isothermal parameter 2 for methane. So it is here you can see 1056. And isothermal parameter 2 for carbon dioxide is here you can see for carbon dioxide it is 1187. So 1187. Isothermal parameter 3 for the methane it is 4.7 multiplied by 10 raised to 4 minus 5. 10 raised to 4 minus 5. Okay, isothermal parameter 1.2 multiply 23 multiplied by 10 raised to 4 1.3 multiplied by 10 to the power minus 4. Isothermal parameter 4. This is for 1067. And here isothermal parameter 4 for carbon dioxide is 1210. Okay. Okay. Specific flow direction, there is no specific, it is 0 and this is given. Okay. Now the bed is fully specified. The bed is fully specified. Now we will go to the value and specification for first node of the bed. So okay, this is fully specified. We will close this one and press on initial. So here you can see the first node, the mole fraction in the first node of carbon methane and carbon dioxide. So here you can see 1 is for the methane and 0 for carbon dioxide. So 1 and 0. Okay, now close this one. Okay, now we will plot the breakthrough curve. So we will click on initialize. So click on this one, click on OK. Close this one. Now go to this section, new form. Click on this one and breakthrough curve. Breakthrough curve for methane and carbon dioxide. So I will this side. Double click on the product. Okay. Here you can see, click on results, and here plot this one. This is methane and this is the carbon dioxide. Now click on this time axis, and the time is, suppose I want this plot from 1 second to 300 second, and the grid interval is, suppose it is 50, and the time window is also 300 second. Click on OK. Now close this one and close this one. Click on initialization and click on this button. OK. Okay, now go to this, click on this button. Okay, click on dynamic, and here click on this button. The time now is 0, and I will pause my simulation after 300 seconds. Check this one, click on OK, and now click on this run button, this. So it will take some time to float. So now the simulation is completed, and here you can see the float. You can see the float. So here you can see that the methane is decreasing. Methane is slowly, it is decreasing. It is adsorbing. It is adsorbing inside the adsorption column. And the carbon dioxide is slowly, after 100 seconds, it is slowly desorbing from the adsorption column. So here you can see after 100 seconds, the methane will adsorb and it will replace the carbon dioxide. The carbon dioxide will desorb and methane will adsorb. The methane, here the methane concentration is slowly, the methane mole fraction here, it is slowly decreasing. It is slowly decreasing in the outside. In the product stream, methane is decreasing here after 100 seconds because it is adsorbing on the adsorbent surfaces. And here you can see after 100 seconds, the carbon dioxide will remove, it will dissolve from the adsorbent. So this is all about the that how can we plot the breakthrough curve of methane and carbon dioxide inside the adsorption column using the aspen adsorption. So you can also plot some other, like this one is for simply this curve is for the carbon dioxide, uh, and this one is for, now if you want to plot one graph, you can also click on this one and click on the property. So this one is for the, this one is for the carbon dioxide, and this is for methane. So here you can also like this one, for example this one, click on OK, or you can see go to property. Okay, like this one, click on this one, click on this one, on this one, click on OK. So go to the property here, like this one. This is the map axis. Okay, map axis all in one. For example, carbon dioxide apply. Okay, go to the property. So here you can see various, like this one. So this is the breakthrough curve. You can also plot some other graphs. like this one, CO2 loading at different point compared with CO2 loading. So CO2 loading at different point compared with methane loading. So you can also plot the loading curves in the next video. In the next lecture we will plot the CO2 and methane loading. Thank you very much for your attention. If you are new to the channel, please like and subscribe.